Hi everybody and welcome to this 9th video of BIOB20. In this video I would like to talk about transforming Gaussian distributions. We have seen how to use the function rnorm to generate Gaussian random numbers. For instance, rnorm equals 5. Now if I'm interested in the square of Gaussian random variables, I can use the square symbol, which is ℏ2, following the rnorm n equals 5 function, and I would get the square of 5 Gaussian random numbers. To know what the distribution of the square of a random Gaussian distribution looks like, we're going to create a relatively large sample of 100,000 Gaussian random numbers that we're going to raise to the power 2. If we now look at the histogram of this distribution, we see that this is very asymmetric, that of course the values cannot be lower than 0, and that most of them are actually close to 0 and very few values are above 10, for instance. Another way to represent this distribution is to use the function density, which is essentially a continuous version of the histogram. We obtain a graph that has the same shape as before, except that the collection of bars has been replaced by a single smooth line. Note that the y-axis does not show the counts anymore, but an arbitrary density function. It turns out that this density is actually a gamma distribution. To show this, we are going to sample a gamma distribution with a large sample size. Importantly, I'm setting shape to 0.5 and scale to 2. Then, to add a new line to the existing graph, I'm using the lines function, and I'm passing the density of y with color 3 for green. And as you can see, the two densities are exactly identical. That shows that indeed squaring a Gaussian random variable is the same as taking a gamma distribution with shape equals 0.5 and scale equals 2. What about the sums of squared Gaussian random variables? In this example, we're taking 5 random Gaussian numbers, we square them and sum them so that we obtain only one number. If I want to do this a large number of times, I need to use the function replicate. I create a new sample x where I use the function replicate with n equals 100,000, and I use the expression that I've just defined before. When I plot the density of x, I get a new shape that is slightly different from the previous one. And we can see that indeed it no longer coincides with the gamma distribution that we had made before. Instead, it coincides with another gamma distribution where we change the shape parameter. I update the shape parameter to 5 times 0.5. If I do this and I overlay the density with the red color, you can see that now the two densities coincide exactly. This particular gamma distribution is known as the chi-square distribution with 5 degrees of freedom. The degrees of freedom of the chi-square distribution is equal to how many Gaussian random numbers you have summed to obtain one number. This is 5 in that case. In summary, the chi-square distribution can be seen either as a sum of squared Gaussian random variables or as a special case of gamma distribution. Next, I would like to talk about logical operations. To have something to work with, we are going to create a random sample from the Poisson distribution. We have seen previously that we can select from a vector using the square bracket notation. If I want the elements above 1830, I say x square bracket, x greater than 1830. The mechanism of this selection procedure is that x greater than 1830 gives a true-false vector, also known as a logical vector. We obtain a value, true or false, for every element of the input vector, x. This works because the true-false vector has the same length as the vector that we select from. In this example, we said that we want to output the first number, we do not want to output the second number, we do want to output the third number, and so on. To give us something to select from, we're going to use integer division. The notation %% gives the rest of the division by a certain number. For instance, for the division by 2, we obtain the following. When the rest is 0, the number is even, and when the rest is 1, the number is odd, by definition. To get a logical vector with the even numbers, I can say x %2 equals 0. I get 2 when the rest is 0, that is to say when the number is even. Now I can use it as a selection for getting the values of x that are even. I can change the conditions to get other selections, like the numbers that are 3 times something plus 1. Now, what if I want the numbers that are 2 times something and also 3 times something plus 1? The solution is to use the logical operator AND, which is that symbol here. I put the two conditions separated by AND, and to make it clear, I isolate each condition by round brackets. I obtain the 4 values of x that are both 2 times something and 3 times something plus 1. Instead of AND, I want either or, I would use the logical OR operator. It's the vertical bar symbol, which on most keyboards is close to the Enter key. I obtain a bigger list because there's only one condition for the number to be in the output. The logical operators AND and OR are really useful when we want to make elaborate selection conditions. Another interesting thing about selecting with logical vector is that sometimes some numbers could be missing. I'm now creating an example with 1, 2, 3, 4, NA. The vector x has 5 values, but the last one is missing. And now let's look at the result of the operation x less than 3. We obtain true, true, false, false, NA. The NA carries through to the result. But what happens when I use this for logical selection? You can see that we get 3 elements, 1, 2, and the last element, which is NA. So when you have missing value in your data, the selection procedure keeps them. So what can you do if you want to remove them? In such cases, you can use the function which. When you call which on a logical operation, you get the indices where the condition is true. Instead of getting true and false, here we get 1 and 2. Those are the positions where x is less than 3. And as you can see, the positions of the NAs are not returned. I can then use the output of which for a selection which is no longer based on a true-false vector, but on a vector of indices. When there are NAs in the input, the function which will remove them when you use it for selection. But when there are no NAs, it doesn't make a difference whether you use the function which or not. Using logical operators and potentially combining them with the function which allows you to make elaborate selection on any vector. Next, we're going to see how to create tables and how to count occurrences. To start with, we are going to create a random binomial sample. We make it with 1000 elements, prob equals 0.5, and size equals 13. If we look at the first elements of x, we can see that they are all integers, as expected. To count the occurrences of each of them, we can use the function table. We obtain the counts of all the values that occurred at least once in the sample. As you can see, the most frequent value is x is equal to 6. We obtain the number 1 only 1 time, and the number 11 9 times. We never obtain 12 or 13. Overall, the function table is really useful when we want to get a count of all the elements inside a vector. We can also use a graph to represent the values in a table. For this, we just have to call the plot function on the result of table. We obtain a plot that looks like a histogram and that is a representation of the counts. In this example, we have seen how table can be useful to count numbers, but the function table is more versatile than just this. We are going to import a new dataset called isof. For this, we type data isof. This creates a new object in the session, a data frame that is called isof. The data describes a cohort of patients and whether they got cancer of the esophagus. If we look at the first rows of this data frame, we can see that it contains 5 columns. The first is the age of the group, the second is the alcohol consumption of the group, the third is the tobacco consumption of the group, the fourth is the number of people who got cancer of the esophagus, and the last is the number of people who did not get cancer. The second and the third columns are not numeric. They are factors, which means that they are qualitative variables. For instance, we can create the table of the alcohol consumption. As you can see, we get 4 different values, which means that there are 4 different categories. Looking at the extremes, there are 23 individuals who have less than 30 grams of alcohol per day, and 21 individuals who have more than 120. We can of course do the same for the tobacco consumption. Again, there are 4 values and therefore 4 different categories. Looking at the extremes, we see that there are 24 individuals who have less than 9 grams of tobacco per day, and 20 individuals who have more than 30 grams per day. What's interesting is that I can as well create a 2D contingency table. For this, I need to call the function table on both factors at the same time. Here, topgp and altgp. I then obtain a 2D table which shows how many times each pair of categories occurs in the data. In this example, each combination of categories occurs between 4 and 6 times. A table is a regular R object, and the rules for selection are exactly the same. For the demonstration, let us assign this table to a variable y. To select the last row, I can do y square bracket 4, comma. Another way to do this is to replace the index by the label of the row. Here I can do y square bracket between quotes 120 plus, comma. And for the columns it's the same. If I want the last column, I can do y square bracket, comma, 4. Or I can use the label of the column, like in y square bracket, comma, between quotes 30 plus. So with a table, I have the flexibility of doing the selection with the index or with the names of either the rows or the columns. Combining these 2 operations, I can also subsample the table, for instance, into a 2x2 table. Finally, we can also plot a 2D table. If I call the function plot y, I get a figure that represents the table with rectangles and squares. Notice that in this representation, the labels of the rows are actually the labels of the columns when we print the table. And vice versa, the labels of the columns are actually the label of the rows when the table is printed. In this representation, the table is first split over one factor which appears in column of the plot. Each column is then treated as an independent 1D table. We can see that the category that is the least represented corresponds to 20 to 29 grams of alcohol per day and 80 to 119 grams of tobacco per day. In the printed table, we can see that this pair of categories occurs 4 times. Another pair of categories occurs 4 times in the table, and we can see that in the graphical representation it has the same size. In summary, this representation can be useful to detect imbalances in 2D contingency tables. That's all I wanted to share with you. Good luck with the quiz, and see you in class.